At 11:42 p.m., the first alert did not come from our application. It came from our security monitoring system. Unusual SSH activity detected. Normally, that alert fires when someone attempts to access infrastructure outside of normal hours. But this time the activity was different. The alert showed a sequence of successful SSH logins to our Bastion host. Then a series of commands executed across several internal servers. Within minutes, Slack started filling with automated messages. IAM role usage anomaly detected. Unexpected database connection from internal host. Outbound traffic spike from private subnet. At first, it looked like a misconfigured script. Then one of the engineers asked a question that immediately changed the tone of the incident channel. Who is logged into the Bastion right now? No one answered. Our infrastructure ran on AWS inside a private VPC. Production services lived mostly in Kubernetes on an EKS cluster, but several internal systems still ran on EC2 instances. Access to those private machines was restricted. They lived in private subnets with no direct internet access. To reach them, engineers had to connect through a Bastion host. The Bastion was a hardened EC2 instance placed in a public subnet. Engineers would SSH into the Bastion first, then use it as a jump point to reach internal systems. Authentication required SSH keys stored in our internal secrets manager. Access logs were collected through CloudWatch and forwarded. The Bastion also had restricted IAM permissions. Monitoring included Datadog and a security system that analyzed unusual authentication patterns. Under normal conditions, the Bastion saw only a few login events per day. The alerts showed that the Bastion host had logged several SSH sessions within a short time window. At first, that did not seem alarming, but the command logs told a different story. Shortly after the login, the session executed a series of reconnaissance commands listing internal host names, checking running processes, enumerating Kubernetes service endpoints. Then outbound connections appeared in the network logs. Traffic leaving the Bastion toward unfamiliar IP addresses. Meanwhile, the production application itself continued operating normally. Customer traffic was stable. Error rates remained low, but the security alerts kept escalating. Suspicious IAM role usage, database connection attempts. Something was clearly happening inside our network. The first step was identifying the SSH session owner. The Bastion logs showed authentication using a valid engineer SSH key, but the engineer associated with that key was asleep. They confirmed they had not logged in. That meant the key itself had likely been exposed. Next, we checked the command history captured through session logging. The commands looked methodical, listing environment variables, searching for credential files, attempting to connect to internal services. At this point, the incident escalated. We immediately restricted outbound network access from the Bastion host. Security and DevOps engineers focused on containment. The priority was preventing further lateral movement inside the network. One concern was whether the attacker had already accessed sensitive systems. Database access logs showed several failed connection attempts from the Bastion, but no successful authentication. That was a relief. The root cause traced back to an exposed SSH key stored in a developer workstation backup. Earlier that week, an engineer had created a local backup archive. That archive included their private SSH key. It was accidentally uploaded to a publicly accessible object storage bucket during a testing workflow. Within hours, automated scanning bots detected the exposed key. Attackers attempted authentication against known Bastion host IP addresses. Because the key was valid and our Bastion still allowed SSH key authentication from any source IP, the attacker successfully logged in. The first action was terminating all active sessions on the Bastion host. Next, we revoked the compromised SSH key from the authorized keys configuration. Firewall rules were tightened immediately. Bastion SSH access was restricted to our corporate VPN IP ranges. We also rotated credentials associated with several service accounts that the attacker had attempted to enumerate. The Bastion host itself was rebuilt from a clean image to eliminate any possibility of persistence. Security teams scanned all internal systems. Fortunately, because of strict IAM permissions and network segmentation, the attacker had limited access beyond the Bastion. Recovery focused on credential rotation. The real failure was not the Bastion architecture itself, but our authentication model relied heavily on static SSH keys. Once that key leaked, the Bastion had no additional verification step. Detection worked well because session logging captured the attack activity quickly. However, the root vulnerability existed because sensitive keys could exist unencrypted on developer machines. First, Bastion hosts should enforce multi-factor authentication or certificate-based SSH rather than static keys. Second, SSH access should be restricted by source network ranges whenever possible. Third, automated secret scanning should run on all storage buckets. Fourth, ephemeral access methods such as short-lived certificates dramatically reduce the impact of leaked keys. Fifth, session logging provides critical forensic visibility. That night reminded us that a single exposed credential can quietly unlock an entire network if the right safeguards are not in place.